Continuing our series on vectors here, we're going to look at cases where vectors are in equilibrium. Here's an example of vector equilibrium. In this question you have three forces acting, 7 newtons down, F, an unknown force at an angle theta to the vertical, and a 5 newton force at 30 degrees to the vertical. Now you can easily do this by taking components because 5 sine 30 pointing out this way will balance with the F sine theta pointing out that way, and that will give you one equation. And you can also add the 5 cos 30 vertical component of the yellow force to the F cos theta vertical component of the F force and put those two pointing up equal to the 7 newtons pointing down, and that gives you two equations. So upward forces equal downward forces since it's in vertical equilibrium. So 5 cos 30 added to F cos theta will equal the downward 7 newtons. And we'll call that equation 1. We also have horizontal equilibrium, so forces to the left will equal forces to the right. So forces to the left is the component of F this way, and that's going to be F times the sine of theta. Forces to the right are going to be 5 times the sine of 30 here. And so we get another equation for the horizontals, and we'll call that equation 2. And we need two equations because there are two unknowns. There's an F value that's unknown and there's a theta value that's unknown. So we need two equations. What we need to do now is to get the F sine theta and the F cos theta on their own. So F sine theta is already on its own. We want to get this F cos theta on its own. And you realize that that's going to be equal to 7 minus 5 cos 30. So that's what I'm going to do. I'm going to take this equation and divide by F cos theta, so I get F sine theta over F cos theta, and I need to remember what F cos theta will equal from equation 1. So I'm dividing equation 2 by equation 1, so my left hand sides are going to be F sine theta over F cos theta, and I need to just find out what the right hand sides are going to be. The F sine theta is dead easy because F sine theta just equals this. And the F cos theta, if I isolate this, I'm going to get 7 minus this. And so we end up with F sine theta over F cos theta equals this thing. Now these are all numbers, the 5 sine of 30 over 7 minus 5 cos 30. These are all just numbers, so this side equals a number. But what's happening on the other side here is that these f's are going to cancel, and we get sine theta over cos theta. Now sine theta over cos theta actually equals the tan of theta. So theta is going to be the inverse tan of this thing. So theta will be the inverse tan of 5 sine 30 over 7 minus 5 cos 30. So we need to take the inverse tan of this thing to get theta. So theta equals 43.1 degrees. So now we can take this angle and substitute it into our simplest equation here to get a value for F. So if I rearrange this equation, F would be 5 sine 30 divided by this sine of theta. So F equals 5 sine 30 degrees over the sine of 43.1 degrees. And that turns out to be 3.66 newtons. So we've got our theta and we've got our value of F. This problem has a lot more forces in it. We're probably interested in breaking everything again into vertical and horizontal components. This one will have a horizontal component and a vertical component. This one will have a horizontal and a vertical component, and we need to formulate a vertical equilibrium and horizontal equilibrium equation. So we'll start with vertical equilibrium. Total upward force equals total downward force. So we've got a 6 pointing up and a 6 pointing down, so both sides have a 6 on them. The upward also has a component of this 8.03, and it'll be 8.03 sine 40 degrees. And the F force has a vertical component pointing downward, and that's going to be F sine theta. So the smarter amongst you will recognise that these two 6's are going to cancel straight away because we have equal and opposite forces there. So that does simplify it a little bit. So, as well as that, we have forces to the left and right that are balancing. And so, we have this 12.3 Newton force balancing with the horizontal component of this 803, which is going to be 8.03 cos of 40, and the horizontal component of F, which is going to be F cos theta. So that's our horizontal resolved forces. So we do the same thing that we did before. We want to get F sine theta and divide it by F cos theta. That'll leave us with only one unknown. So when we divide these, F sine theta is equal to this 8.03 sine 40, and F cos theta is going to be equal to 12.3 minus this thing. So, as before, the f's now cancel, and sine theta over cos theta gives us the tan of theta. So, the tan of theta equals 0.839, and theta equals 40 degrees if we take the inverse tan of that. And that makes sense because this is a symmetrical system. These forces are symmetrical. This one points along this line, so these two are going to have to balance each other in the vertical direction. And you can see if we substitute in this first equation that the sine of theta, if theta is now 40, the sine of theta and the sine of 40 have the same value. So if they're the same value and they are cancelled out, then F must equal 8.03. So we end up with a totally symmetrical pair of forces, 8.03 up and down. Right. Here we have another object in equilibrium, and we have an unknown force at an unknown angle to find. Again, we take components in the horizontal and vertical, and we do upward forces equal downward forces equilibrium equation, and we do forces to the left equal forces to the right equilibrium equation, and then we again solve it for the unknown force and the unknown angle. So we have upward forces equal downward forces, and that gives us 6 newtons cos 20 because it's an adjacent component here, plus F cos theta, and they both are battling against this 9 newtons. So 2 upward forces, 1 downward. And also we have forces to the left equal forces to the right because it's an equilibrium that way as well. So 6 sine 20 equals F sine theta. And then we do the same old trick where we take the F sine theta divided by F cos theta. And so F sine theta is equal to 6 sine 20, so that goes on the top line. F cos theta, here it is, it's going to be equal to 9 minus 6 cos 20. So we get this expression here for the tan of theta. The f's cancel and sine over cos gives us tan. So theta is going to be tan to the minus 1 then of 6 sine 20 degrees over 9 minus 6 cos 20 degrees. And that gives us 31.4 degrees. So we can just substitute back into this, which is the simplest of the two equations, to get f. F is going to be 6 sine 20 over the sine of theta, and that becomes 6 sine 20 divided by the sine of our value for theta, which is 31.4. And that gives us 3.94 newtons. This question involves the equilibrium of a rigid rod sticking out from a wall and being held up by a cable. You can see there's a 200 Newton weight here at the end of the rod, and then the cable holds it up. The rod presses out with a compressive force, and you can see here that the three forces all pass through this one point. So you can imagine this is a single point in equilibrium with these three forces acting through it. Resolving vertically, we have a vertical component of the tension, vertical component of that acting up, and the 200 is the only force acting down. So we get T sine 30 equals 200. We'll call that equation 1. And there's horizontal equilibrium as well, so forces out to the right will equal forces to the left. To the right we've got F, and to the left we've got a horizontal component of T here. T cos 30. So from equation 1 here we can see that T is going to be 200 over the sine of 30. And that's going to be 400 newtons. And so we can substitute into the other equation now and say that F equals 400 cos 30. And that gives us F at 346 newtons. Here we have a similar beam problem where there's a rigid beam like this and a cable pulling like that. 300 Newton downward force. Again, T will have a horizontal component that's being balanced by F, and it will have a vertical component that's being balanced by the 300. So T sine 20 degrees, which is the vertical bit of T here, is going to be equal to the 300. And we'll call that equation 1. Forces to the left equal forces to the right as well. And so F is going to equal T cos 20 degrees. So from this first equation, T is going to be 300 over sine 20. And that turns out to be 877 newtons. And now we can substitute that back into our other equation here. So 877 cos 20 should equal F. And that comes out to be 824 newtons. And that's it.